All right.
So thank you guys for staying with us. Our next speaker is Wangmo, who is a final year PhD student, getting very close to the end. She comes from industry experience with a background in power engineering and is passionate about green and sustainable energy research. So Wangmo, I'll pass it over to you.
Thank you, Molly. I'll start on sharing my screen. Okay. Do you have my screen up?
Yep, we can see it.
Okay. Good morning, everyone. Thank you, Molly, for that introduction. And as Molly introduced, I'm a final year PhD student. My research is supervised by Professor John Bell and Associate Professor Andreas Helwig. The research industry partners are ERC Research Hub for Safe and Reliable Energy and Zero Emissions Development. Well, the main research topic is battery-supercapacitor energy storage system fatigue investigation for grid ancillary services. I know it's quite a mouthful, but what it is essentially just a hybrid energy storage system between battery and supercapacitor. And the research focuses on the degradation or the fatigue side of the hybrid energy storage system when these systems are supplying energy for grid ancillary services. And grid ancillary services are those services which are acquired by power system operators in order to operate a power system at a stable frequency and voltage as being allowed by the grid code. So that's the simple explanation of this mouthful topic. Here it is. While going briefly or brushing through the backgrounds, literature review, objectives, and methodology, the primary focus of this presentation would be on the beginning of life assessment and findings and way forward. Now, when I say beginning of life assessment, means that when battery and supercapacitor in a hybrid arrangement, when they are new or in the initial state, how do they behave? And this really becomes the foundational premise in order to later on then evaluate or assess the evolution of the performance when the same system approaches end of life. So this would be the main focus of this presentation today. Well, some background first. I believe energy is such a topic that sparks everyone's interest, especially when we are, intricate part of this, when energy tariff rates keep on rising, and whether we like it or not, we are intricate part of this. So what is actually happening in the power system globally or energy globally is there is a scene in the increased renewable penetration, and the reverse trend or the inverse trend of decreasing non-renewables. And this is a global phenomenon because of the target to reduce the global emissions. But in Australia, the renewable energy growth has seen an increase from 14.6% in 2015 to 32% in 2022, and the inverse reduction in the fossil fuels from 85 to around 60% in 2022. And today, the energy mix of the national electricity market as of May 2025, the instantaneous penetration stands with the maximum penetration from the renewables being 70% and the rest 30% from non-renewables. I mean, this is not a bad thing, obviously, because it is consistent with the global target to increase the green energy sources, right? But the question really is about how ready a power system is to balance such a dominated renewable energy, because without a proper balancing services and system, what you see is an increased instability in the power system. What you see on the bottom left graph is what they call it as a duck curve in the electricity market. And what it essentially shows is that during the daytime, when the renewable energy, particularly in case of Australia, the PV generation peaks during the midday or during the actual sunshine hours, the demand from the grid is very low, and this minimum demand keeps on reducing further. Please note that the minimum demand value that is shown in here, which is 11 gigawatt, is not the minimum. The graph is just an illustrative purpose to show what does it mean to have an increasingly growing difference or the gap between the maximum and minimum operational demand. So what you see is a reduction in the minimum demand from the grid during the midday, but in the evening or during the mornings when the solar or the renewable energy availabilities are minimum, but again the peak load increases, then the demand from the grid picks up, and there is almost an increasing or a rapid ramp up that is required from the grid. And these kind of sudden shoulder load ramp ups coupled with the unpredictability of weather conditions is what is leading to more unstable power system and also increased grid failures. And in order to balance these services, balance such a service, the need for services such as the grid ancillary services for frequency and voltage control keeps on increasing. And in Australia, the dominant grid ancillary service is the frequency control ancillary services. For these frequency control ancillary services, the requirement is that the service provider has to respond within a very fast response of 1 second, and a fast response of 6 seconds, followed by a slow response of 60 seconds, and the longest being 5 minutes, which is called as the delayed response. So you can see from here that the service provider for such ancillary services does not, is required not just only to provide that energy demand, but also have a fast response capability. And a battery energy storage technology with that advantage of a medium energy storage and a supercapacitor that has a fast response capability, and the combination of the two is what is a prospective solution for this kind of services. And the difference between a battery and supercapacitor for that kind of energy and power delivery is in its energy storage mechanism, where the battery is based on the electrochemical reactions to store and then discharge energy, whereas for the supercapacitor, it is based on the electrostatic charge separation and then accumulation on the respective electrodes and electrolyte interface. So that gives us the difference between energy and power delivery, and therefore the combination of the two is very fitting for this kind of ancillary services. But the question is, out of so many battery technologies, what is the recommended or what is the optimal choice between all of these types? Although I would not want to go into more detail into this, but just wanted to point out this paper, which has more relevant information. But from this, what I would like to point out is, out of the so many battery technologies, lithium-ion battery, which comes under the category of metal-ion batteries, is commercially more applicable as well as used for this kind of stationary energy storage technologies. And also, when it comes to supercapacitors, there are, again, different types of supercapacitors, and I would not want to go into details, but the commercially available supercapacitors are what they call it as a symmetrical electric double layer capacitors, or some call it as supercapacitors and some call it as ultracapacitors. So there's so many synonyms into it, but I'm going to refer these as supercapacitors here and after. So, but the question is, why are we investigating on the FETIC side of it? And it really is about, irrespective of the battery technology, all of these energy storage technologies are interfaced or connected to the grid through power electronics. And the way they are interfaced, or the power electronics transfer energy from energy storage technology to the grid, is using a technique called pulse width modulated control, which is essentially a rapid switching on and off of the IGBT switches in order to then efficiently regulate the current and voltage on the grid side. And the switching frequency is usually up to about 20 kilohertz. And therefore, this kind of fast switching would then introduce a frequency ripple that are quite different from the DC or the constant current. And the graph below here illustrates that difference, where the constant current is a constant magnitude and then constant duty. But in the graph that shows PC is what is essentially a pulse current, which is a rapid switching on and off, and therefore there are a lot of rapid transients in that method. And therefore, it raises a really important question as to whether these rapid transients affect the battery. And if it does having a supercapacitor help because of the common knowledge that supercapacitor is, have the inherent characteristic to respond faster than the batteries. And the way to evaluate their performance is through capacity fade and the internal resistance increase throughout this process. And the existing literature on such impacts, I would say, is quite inconsistent and also rather vague, because one of the studies in by Udin and his counterparts in 2017 on NCA chemistry said that with the increasing frequency, there is both capacity fade as well as increase in internal resistance. But again, another study, obviously on a different chemistry though, indicated that these kind of ripple currents actually doesn't negatively impact, however, but actually does have a positive impact. And another study on an MC chemistry at also 5 kilohertz switching frequency said that there is a slight capacity fade because of high frequency switching or the ripple currents, but on a condition that this only happens on the partially discharged cell and not on the fully discharged cell. So you can see that there are so many factors that influence these findings, and obviously researchers have their own objectives. They follow different procedures, current ratings, frequencies, different chemistries, and therefore I'd like to conclude in the battery side that there's inconsistent findings and limited research in terms of long-term aging due to high frequency of the pulse discharge. And similarly, on the supercapacitors, the common knowledge is that supercapacitor is able to handle that high frequency. And one of the studies does show that it has no significant impact due to that kind of high switching frequencies. But again, there are not many research that can incur this. And also the commercial manufacturers for such supercapacitors, which are Maxwell's and Eaton's, they do kind of indicate or insinuate in their technical guides that due to pulse current, there may be a reduction in efficiency. For example, in Maxwell says that there might be a reduction in efficiency due to internal resistance, and obviously internal resistance is linked to the thermal stress on the components, so which may then infer that there is a capacity fade or the degradation on the supercapacitor. And Eaton again says that the ripple current is not recommended if the surface temperature of supercapacitor increases by 3 degrees Celsius. So therefore, there is yet again limited knowledge and presents further research opportunities in terms of both batteries and supercapacitors. And which is why then it brings me to these main research objectives where the objective is to answer whether the battery and the supercapacitor, how do they share load at the beginning of the life, which becomes the foundation of the study, and then how does that differ when they are, going through the cycling process and approach their end of life, which becomes the hybrid case degradation model. And then third objective is a benchmark case when it's just the battery alone going through the same cycling process, so that this becomes a comparison case against the hybrid case, and then which would then answer if the supercapacitor is aiding that or not. And ultimately, then be able to answer or bring out the optimal principles that will maximize the life cycle of such energy storage technologies when they are providing the frequency control ancillary services. Well, that brings me to the methodology, and as you can see from this flow chart, it is a combination of both experiment as well as modeling. And please refer to the legends to indicate where I am at this stage of my study, where completed boxes are green, then orange showing the ongoing activities, whereas the dark blue shows some of the way forward activities. And the methodology really is first initially basing the capacity and internal resistance measurement at the constant current, and then carrying out the pulse discharge experiment at the frequencies that I've indicated earlier, that is about close to 20 kilohertz, and then continuously cycling the energy storage technologies in order to then see the degradation. But again, in the continuous cycling or the longitudinal experiment, there is again a periodic capacity and internal resistance measurement, so that it gives us a relation or the trend with the increasing cycle numbers and increasing the duration of the cycling. How does the capacity and ESR change? And then this will reveal the degradation or the fatigue mechanism aspects of the hybrid arrangement. Well, going on to the main focus of this discussion, which is the beginning of life assessment. So the slide here indicates the schematic of the experiment in which the battery and supercapacitors are connected in parallel, both of them connected to V1, which is the common supply to charge the system. And again, E1, which is a common electronic load to discharge the system. And again, the whole of the experiment is driven by the National Instrument and LabVIEW software. The same is shown in here in a photograph where battery and supercapacitor will be sitting here, then charged by the common supply, then discharged by the electronic load, the sensors to pick up the current and voltage of the individual components, and then, like I said, the control and the data acquisition software that drives the whole experiment. And here's more details into the type of battery and supercapacitor cases that I've looked at, which will then be a reference for the rest of the discussion in here. The first image shows the lithium iron phosphate battery, which is a type of in the category of the lithium ion battery, as I indicated earlier. And when the lithium iron phosphate battery is just sitting alone, this becomes a base case. Whereas when the lithium iron phosphate battery is connected in parallel to the Maxwell supercapacitor, this becomes case 1. And when the same battery is connected to the Eaton supercapacitor, that becomes case 2. And I guess the most important parameter or the characteristics to look out for in this slide is the internal resistance, because the common knowledge is that the higher the internal resistance, the higher the voltage drop and slower the response. And then this reveals a lot about the dynamics of each individual components and how do they affect as a combination. Also, please note that in each of the cases, the current ratings are as indicated in the discharge current below, which is 7 amps at the standalone case, but 10 amps at the hybrid case. And the reason being that the battery is rated at 7 amp hours and the maximum discharge current recommended is 7 amps. And the main objective of this research being to see the influence of the frequency. I am limiting the other factors like going beyond the current ratings. So limiting that to 7 amp hour, but because in hybrid arrangement, the supercapacitor would be taking certain portion of that. That's why I'm able to achieve a little bit higher current rate for the hybrid arrangements. Well, into more details about the data analysis. So in the data analysis, the first graph that I put in here is the current sharing dynamics. And I wanted to focus on this at the first starting point, mainly because I believe that the rest of the phenomena or the subsequent phenomena that I'll be discussing is closely related or influenced by this dynamic. So what you see in here is that a peak current sharing between battery and supercapacitor, and that is plotted against the voltage with the increasing discharge time. So what you see is initially the supercapacitor is able to handle that initial surge at the high state of charge, and battery is able to quickly ramp up until battery reaches the steady operation, which is when then the supercapacitor is steady and doesn't pick up that surges. And therefore, what you see is a proper transition between battery and supercapacitor until battery operates in a steady operation. And the graph in here is obviously a sample at one frequency because we are looking at different frequencies. But because there is only minor difference in different frequency, this serves as a discussion for all the other frequencies. But on an average, supercapacitor shares about 60% in the beginning. And then during the steady state, it shares about 20%. And the inverse trend where then the battery shares about 30% in the beginning, and the battery picks up that higher range and remains at 70% steady operation. And this is the current sharing dynamics applicable to all the cases, irrespective of the supercapacitor type that we have tested. And because of that current sharing dynamics, what you see in here is the peak load current reduction in the lithium iron phosphate battery is being tested. And the idea is that if the peak current that is experienced by lithium iron phosphate battery on its standalone is quite different from its in hybrid arrangement, and then that is where we can speculate the combination or the contribution from the supercapacitor side. That's why what you see in here is first the base case where the peak current in the LFP is quite higher as compared to the LFP peak current in the hybrid arrangement. And the hybrid arrangement in case 1 with Maxwell supercapacitor shows about a reduction of current about 42%. And similarly, when I'm basing the same base case and comparing with the second hybrid case, then you can see that there's a peak current reduction of 46%. Now, I'd like to bring your attention here from the earlier slide where I said that the ESR determines how the components behavior or the response contributes to the energy storage behavior. And the usual or common knowledge is that ESR is a representative of how quickly energy storage technologies respond. But please note that whatever the ESR that usually manufacturers give out is ESR at constant current, and it is not representative of the dynamic behavior at high frequencies, and which is what it is revealing in this, because the Maxwell supercapacitor obviously has a lower ESR, and the expectation is it will be able to reduce higher peak current more than the Eaton supercapacitor, which is not what we have seen in here. Therefore, it reveals the high frequencies dynamic behavior, which is quite different from the constant current behavior. And the second aspect that we're looking at is battery energy contribution. And again, going back to the supercapacitor's contribution to the battery is the main objective in here. And what we have looked at is what is the energy being extracted from the battery when the battery is just supplying to the load alone, whereas the battery is sharing load with supercapacitor, and then the combination of two is supplying to the load. And to illustrate in here, I've looked at the energy contribution at both PWM on stage and PWM off stage. PWM on stage is when the load is enabled, and PWM off stage is where the load is cut off, right? And the expectation is that during PWM off, the current would be 0 for battery because it's not operating. But you can see that during PWM off, battery is actually not sitting idle, but it is recharging the supercapacitor back, which is what it's shown in the graph in here. And looking at the combination or the gross energy contribution of the lithium and phosphate battery in case of both PWM on and PWM off stage, what we see is that the battery in a standalone contribution energy is quite low as compared to hybrid, and then this would mean that maybe battery is stressing more because of the recharging the supercapacitor during PWM off, then which would then reveal that it is not actually serving the intention of the hybrid arrangement. But please note that the current rating of the hybrid and the standalone systems are quite different. And by factoring into that current proportion, what we see is then the lithium iron phosphate batteries energy being extracted from the standalone case is higher and higher than the hybrid arrangement. Then from this, what I would like to theorize is that there is a net energy reduction of the battery, which would then point out to potential reduction or the degradation or life extension of the lithium iron phosphate battery because of the hybrid arrangement. The other factor is on applicable or relevant to such energy storage technology, especially in the batteries, is the thermal stress. And during the discharge process, thermal stress were being extracted and looked at, and how does that impact or differ from a standalone versus a hybrid arrangement. And what you see here is that in the LFP alone case, the battery's temperature rise is in 1%, whereas in the hybrid arrangement, the rise is 3%, is slightly higher, but on an actual temperature points, what you see is that the maximum temperatures reached during the whole discharge period is still very low compared to what is allowed, or the data sheet allows as a operating or the normal operating temperature range, which is 60 degrees in lithium iron phosphate battery versus 65 in supercapacitor. So I would say that there is negligible temperature increase in this process. However, the longitudinal experiment with continuous cycling would reveal more aspects into it. And then taking into those current sharing experiment data and then fitting into the model using a MATLAB simulating environment is what you see in here, where battery and supercapacitors are represented by equivalent circuit models. And in here, at the beginning of life, the model using a lithium iron phosphate batteries model from MATLAB, which is a standard model. And I believe that for battery technology, the equivalent circuit models are quite established in MATLAB. So I'm going to take directly from the MATLAB. But for the supercapacitor, as there are varying equivalent circuit models for high frequencies at the beginning of life, fitting using a what they call it as a two-network RC model is what I've done at this stage. And as you can see, the simulated versus the measured current and bus voltage plots quite fits and complements at the beginning of life. And what will happen at the end of life is then the resistance and capacitance, which are dependent on the voltage, would then evolve and change depending on what the longitudinal experiment shows. And that will ultimately give us the fatigue or the degradation model. So that's the overall of the beginning of life assessment at a comprehensive discussion of both the data as well as modeling. Before I go, I put this slide just to open up or extend further discussion, even though I did not really introduce this earlier. What you see in this graph is a sodium ion versus lithium ion battery. And the reason for seeing this is sodium-ion battery is, a growing interest in the research area, mainly because it is explored as a contender for lithium-ion phosphate battery due to similar chemistry, but also sodium-ion is, abundantly available, and that would mean that it will be more economical to choose a sodium-ion versus lithium-ion if they are, performing. If the performance are, quite comparable. So also the sodium-ion battery that I'm discussing in here is a proprietary battery of the industry partner. Therefore, I would not want to reveal much of the chemistry, but just wanted to open this discussion because it's interesting to note that in the left-hand side is a graph saying that sodium-ion battery versus Eaton supercapacitor and looking at how they are sharing current. And on the right-hand side is the same supercapacitor, but sitting in parallel with the lithium-ion phosphate battery and how they are sharing current load. And you can see that with the sodium-ion battery, there is a constant, steady parallel sharing between the two. Whereas with the lithium-ion phosphate battery, there is a proper adaptive or a dynamic transition between the current being shared between the two. And this is very telling of the inherent discharge characteristics of the both, where sodium-ion battery has this linear drop in discharge curve, whereas the sodium-ion battery has a flat plateau. But at the beginning, there is a triggering point, which is an exponential zone, which is why the supercapacitor is able to pick up that point and share more. And what is interesting in here is it extends more research opportunities as to whether the sodium-ion battery is applicable to frequency control versus the lithium-ion phosphate batteries applicable to frequency control systems. And with that, I'd like to conclude by saying that it does reveal that the supercapacitor is able to reduce the peak current on an average 42 to 46% from the standalone cases. And there is a possible reduction in short-term energy rating for the battery due to supercapacitors sharing, looking at both PWM on and off energy. But the longitudinal experiment would reveal more into this phenomenon of current sharing for the longer time. And temperature rise is slightly higher in the hybrid arrangement, but very negligible. So there is, in that short-term discharge experiments, the temperature rise is, it's quite negligible to say or predict or anything at this stage. But from the final slide that I've looked at, which is the lithium-ion phosphate and Eaton's sharing versus the sodium-ion and Eaton's sharing, it does kind of reveal that the lithium-ion phosphate battery with Eaton is more applicable to short-term frequency control ratings, where you see that fast response of 1 second and 6 seconds response, whereas for the sodium-ion battery in Eaton, it does point out to more applicability at the longer time frequency control or peak shaving aspects, where you don't have to readily respond or within that short rating, but manage that energy delivery for a longer period. And the way forward for this is that ultimately all of the experiments that predict or kind of insinuate at this beginning of life will be validated through the longitudinal experiment, in which the two cases of lithium-ion phosphate versus Eaton will be benchmarks against the lithium-ion phosphate alone case, and then that will give us the end-of-life model for this hybrid arrangement. Well, that brings me to the end of this presentation. But before I go, I'd like to just acknowledge the contribution, obviously, from research partners and also my research supervisors. But I would like to particularly emphasize the contribution from Brett Richards and Richard Landers, who have been instrumental in supporting me throughout this experimental setup, which they are still helping out with the longitudinal experiment. So I just wanted to, acknowledge their contributions. With that, thank you so much. I welcome your questions, but more than that, I would also welcome your, suggestions if that helps strengthen my research. Thank you.